One fellow says, none of them are dimensions, they are number lines. Oh, no, that's what I said, I'm sorry. And he said, many misunderstandings here. It's clear from that statement you don't understand what a dimension even is. Okay, I don't know what a dimension is. Number lines are dimensions. States of being are dimensions. Any descriptive term is a dimension. At least could be. And these are what dimensions are, or what a dimension is. Okay, so this fellow says that dimensions everything. Dimensions are anything you can think of. They just put them in there and say anything you can think of, at least any descriptive term is a dimension. State of being.
Color could be a dimension.
Yeah, everything. Even God is a dimension. So the problem here is, again, people don't define their terms, and then you tell me that I don't know what dimension is. Okay, so let's educate this fellow. Okay, let's find out what he doesn't know. Okay, here's the first one. Here's the definition of dimension. This is from the official literature out there. One is from the Wikipedia, the other one is from Wolfram. They both basically say the same thing. First thing is they clarify that dimension is of a mathematical space, whatever that is, or object, and the other one says dimension of an object. So we're more or less on the same, in the same ballpark here. And then it says, the first one says, is informally defined as the minimum number of coordinates needed to specify any point within it. And the other one says something similar, says, is a topological measure of the size of its covering properties. Roughly speaking, it is the number of coordinates needed to specify a point on an object. So they're both saying the same thing. It's the number of numbers, because that's what a coordinate is. Here we see what the definition of coordinate is, more or less. Let me get this up here. And so a coordinate system is a system that uses one or more what? Numbers or coordinates. So what is a coordinate? It's a number. To uniquely determine the position of the point or other geometric element on a manifold such as Euclidean space. So what do they say? They say it's the same thing. It's the number of numbers needed to specify a point. That's essentially what a coordinate and a dimension is. They're synonyms. There's no difference between the word coordinate and the word dimension according to these people. And there you see the Wolfram says a set of variables which fix a geometric object if the coordinates are distances measured along perpendicular axes, right? And they're talking about distance traveled, meaning what? Number lines. They are known as Cartesian number lines, but they call them coordinates.
Dimensions equal number lines?
Yeah, essentially, not really. I'm going to specify that right now, clarify that right now. And so what is a coordinate? What is a dimension? Number of numbers. That's all needed to specify a point in Euclidean space. That's more or less what it is.
On a grid.
Yeah, on a grid or whatever. And so here we have what it really is. I mean, for the purposes of physics, we're doing physics here, right? We don't care about math, okay? So here we're doing physics. And here you see the differences between physics and math. The ones on the top, physics. The ones on the bottom, the one on the bottom, math, okay? Dimension, length, width, and height, okay? That's it. 3 dimensions. You want 2 of them, length and height, length and width, no problem. Width and height, we'll go with that. But what do they talk about? They talk about, or what do they refer to? Orientation of an object. How it looks, from given how it faces, in other words. Coordinate has to do with locations, and you can see the arrows point in the opposite direction. They point towards the object. You have, for example, a room, and you're going to locate that object within the room with these so-called coordinates, right, that we use in physics. And what are they? Longitude, altitude, and latitude. And then vectors, what are vectors? They're direction of motion. We have motion there, and again, it's outwards. It's the 3 mutually perpendicular directions that an object can move in. And there you have depth, breadth, and elevation. None of those are quantitative. They're only qualitative. They have only 2 properties, and that's direction and perpendicularity, orthogonality. What does math use? Does math have any use for these qualitative notions? Absolutely not. What math uses is number lines, and all they have is magnitude and direction. The problem with direction is that direction is a qualitative concept. Math has no use for qualitative concepts. And so really all they have is this thing they call number line. And they call them dimensions. Sometimes they call them coordinates, and they call them vectors. It's all the same thing to mathematicians. So all I can tell you is that, math does not use dimensions at all, or coordinates for that matter. They use number lines. Everything in math has to do with numbers, only numbers. So they use the word dimensions, and they call them length, width, and height, and then immediately they put some number in there talking about how much, how long, how far, that sort of thing, how much time. So that's how all these number lines have become dimensions and coordinates. Okay, next issue. So we move along here. Paul says, if I drop my computer causing damage, do you think mathematical descriptions damage the computer, or do you think forces did the damage? And he says the same thing for the other one. Says, or do you think field did the damage? And the same thing for computer. He says, do you think energy did the damage? And so he's talking about forces, fields, and energies. And he says they are physical. Physical? What do you mean physical? What does physical mean? And of course they don't define physical ever, so they can use these words. They can say forces, fields, and energies are X. And as long as they don't define X, you don't know what they said. That's the issue. Okay, and it says, far from being conceptual, only residing in the mind or minds of humans as abstract ideas. So that's what he thinks are concepts, right? Concepts is just what resides in the mind. Okay, yeah. If you define a concept that way, then you can get away with anything, because that's not a good definition. What do you mean reside in the mind? Does a tree fit in your brain? Is that what it is? That's how it resides in there, So you got to define really what concept is, and that's not a rational definition. Certainly it's the one he just copied out of a book, a dictionary or whatever, and he calls it, this is the definition of concept. Even to this day, philosophers, like at the Stanford Encyclopedia of Philosophy, are debating what the hell is a concept. Okay? And we have a problem, because here you have these are definitions that you find there. Here's the one for force. Okay, strength or energy as an attribute or action of movement. That's out of Oxford Dictionary. Force and influence. That's what it is. Influence. I guess influenza. When you get the flu, that's a force that can cause an object to change its velocity. Okay, so that's what force is. What is field? Field, a physical quantity. So we're talking about a quantity. Okay, so that's what a field is. He says it's physical. Can we say that a quantity is physical? And it says represented by a number. Okay, so a field is always a bunch of numbers. That's all it is. And what is it that has a value for each point in space and time? So all they're saying is you look at the strength of the field. That's essentially what they look at, and they put numbers in units that extend ever weaker from the farther they get from ground zero. Okay, and so that's a field. If you take all those numbers put together, that's a field. So it's a bunch of numbers. Field, the influence. That's according to dictionary.com. The influence. It's an influence. That's what a field is. Of some agent, whatever agent. It's like the agent doesn't count, or that field is not an agent. It's just the influence of the agent, right? As electricity or gravitation. Considered as existing at all points in space, right? Because it's just a bunch of numbers. They just talk about the strength of the field, not the field itself. Field is the whole thing. It's a bunch of strengths, you could say, a bunch of numbers with units. And defined by the force it would exert on an object placed at any point in space. And then what do we have? We have energy. What is energy? Well, here we have it. Our good friend Richard Feynman, Nobel Prize, right? He told us what it is. It is important to realize that in physics today we have no knowledge of what energy is. Had no clue whatsoever.
Well, it's vaguely defined.
Well,
so
yeah,
obviously
right. That's right. Well, you can see how it's defined. Energy, the capacity. And then you look at it, elsewhere it says energy, the quantitative property. So no, these things are not physical, as this fellow suggests. And absolutely not. They're not, we don't have any physicality to these concepts. These are concepts, and concepts are not what is in the mind. Concept is simply a relation between two objects. Okay? And who performs it? A human. Without humans, we have no concepts really out there. We created all the concepts. Mother Nature did all the objects. We did concepts.
Yeah.
Okay, that's the way it works. Okay, another fellow along the same line talks about field. What is a field? Well, a field is a movie, he says. Yeah, agreed. It is a perturbation.
Perturbation. Whoa. That's a nice word.
Oh, yeah. I'd like to insult you. You're a perturbation. Force is not energy. It is the opposite of energy. It is the loss of energy. Okay? Ether is not a movie, though. It is non-Cartesian, and he says it's pure potential.
Ooh.
Okay, so ether is just pure potential. So he's saying
you know why it's pure potential? Because whatever you need, he pulls it out of the potential bag.
Yeah,
ether isn't until whatever you need. Then you need dark energy. Ether made the dark energy. What else do you need?
Yeah, but even in that case, ether is misconstrued.
Oh yeah.
Yeah, because ether is not just energy or movie or not a non-movie or potential, whatever you want to call it. Ether was a medium, right? That was always in motion. It was ether means air.
Wait,
Greek
a
air.
medium that's in motion?
Yeah, that's it, here it is. In fact, we have it illustrated for you, so you don't have to break your heads.
It's not a fart, is it?
There it is.
It is a fart.
Yeah, there you have it. That's what the ether is. A bunch of particles that was out there, and the movement of that was after Robert Hooke came up with the wave notion of light. After that, the light was simply the undulation of the ether. And what was it? A bunch of particles that are moving up and down. That's what it was all the way to the end of the 19th century when relativity and quantum mechanics overthrew the ether, supposedly. All they did was really change the name because we still have the false vacuum in quantum mechanics, and we have in relativity what is known as space-time. What is space-time? A point at each, an event that happens at each point in space-time. That's what space-time is. And there you have it, each point in space-time. And what they do, they move around. When they move up and down, you have what is known as light, wave nature of light. Okay? So that's essentially what it's always been, a bunch of particles. That's all that ether was ever since the days of the Greeks. Nothing has ever changed. And all those people say, Bill, you don't know what the ether is. Well, but you never tell me what it is. Don't tell me what it ain't. Okay? I want you to tell me what it is. And if it's a what, if it's a thing, point to it. Give me a picture of it. And if it's a concept, define it. Very simple. You either define or you draw. And they never do either one. They say, well, you don't know what it is. Yeah, I know. I'm ignorant. As you're going to show me today, right?
Nope. I'm here to ask them hard questions.
Oh, Jesus. Okay, you'll see. I'll get you. No plate of soup for you today. Okay, here we have another fella along the same line. Let's replace space with the black sky. This guy's going to talk about the ether also. In the black sky, there are many bright dots that we call stars or planets. Okay, the black sky, instead of being empty, is full. It is an object. So the black sky, space, he's saying it's an object, a thing. Okay. If it is, draw it. That's what I say, and tell me what gives it shape, what's the background, right? Elaborating on Bill's hypothesis, threads and ropes, the black sky is all that mass of threads and ropes that are not structured like an atom. So he's saying you have the atoms, right? That's what we call matter. And we have the rope, which everybody calls energy, the vibration of the ropes, frequency times wavelength, right? And he's saying that these ropes, they form this backdrop, right? And he says it's the ether, okay? The word ether, the medium that connects all objects, is an object and not nothing. Okay, so he's saying that ether is an object because ether is all those ropes. Maybe he includes the atom, maybe he doesn't, but I think that's irrelevant. But at least the ropes are included, right? And saying all the ropes, that's the same thing as space, and that's the same thing as ether. It's all one shebang, same thing. And yeah, we have a little problem with what he's saying because here you can see a little picture that synthesizes the problem. Here you have a bunch of ropes going in every direction, right? And the question is, what's the black stuff that gives shape to the rope? If the ropes, all the ropes together, just the ropes, right? That's the ether and that's space. And so what's the black stuff that gives shape to each individual rope? That's what he's got to identify, the black stuff. And he can't say the black stuff is space because he's saying that the ropes are space. That space, ropes, and ether are all the same thing. One and the same. He's saying that the ropes cover every little bit of space, and that's what the ether is. Okay, so that's his argument. And we're saying no, because you have to have two things here. You have to have the black stuff that gives background to the green stuff, which are the ropes. So you got to identify what the black stuff is in this case. And I don't think he would understand anyways, what the issues are here. So, all I can do is just throw that out there for him to answer the question. Okay, moving on here, we have another fellow also talking about the ether, and he says about ether is not space. Okay, we have one that says it is space, this one says it's not space. Okay, space is ether's shadow.
What? What?
So it's so when we have the vibration of the ether, the wave, okay, the electromagnetic wave. He's saying that's a shadow that's moving. Okay, it's a shadow. Okay, and I guess you have light casting on this ether thingy. He creates on ether and gives you the shadow, which is space. The space is what's the shadow. Okay. Okay. So what's the ether then, right? And ether cannot be pointed to because it has no Cartesian. I don't know what that means, because if you should be able to point to it if the ether casts a shadow, which is space, right? So if space is the shadow of ether, ether had better be a thing like a tree, then you can cast a shadow. Otherwise, you can't have a concept that casts a shadow. And he says ether is not a concept, nor is it an object. Okay, so he killed me. I don't know.
He has a third category.
Well, he's got to identify what category it falls under. Okay, all concepts and objects are either perturbed.
I mean, you either have shape or you don't.
Yeah,
but the third one.
Yeah, but that's
kind of maybe have shape when you need it, but not having shape when you don't.
It's what these people never define their terms. That's why they get away. They murder.
The whole point is they specifically don't define it so that they can get away with murder.
But they don't realize how important it is to define words. They think that's word salad and semantics and grammar. And he says, I came here to do physics, not to do semantics, Okay, another fella talking about plasma. Okay, here we have the plasma. Is the fourth state of matter. The famous state of matter. Electrons in a solid, liquid, or gaseous sample of matter stay with the same atomic nucleus. Okay? And what happens when you excite them? Heating a gas will form a plasma. Why? Because electrons are ripped away from the atoms, forming an ionized gas. So what is ionized gas? Means that you're going to strip an electron away from them through some process. That means the plasma, which is a bunch of ionized atoms, right? Means that they're excited somehow by something. We don't care about that at this point. We just care to what is the plasma? And the plasma is an ongoing process. It never stands still. So you can't take a picture of plasma and say, oh, I took a picture of plasma. No, you did not take a picture of plasma. Okay, once you take a picture, that's not plasma, because the word plasma means something in motion. And what I'm staring at is not in motion. Okay, so we got a problem with a picture that you took of the plasma ball saying, hey, that's plasma inside there. No, that's not plasma, because plasma is always in motion. Plasma is a movie. It's never a photograph. Okay, that's the way the word plasma is defined. And it takes 100 years for these people to understand that. Plasma is a form of matter in which electrons migrate. Yeah, they're constantly migrate around the nuclei of the atoms. So plasma is always in motion. If you take a picture of plasma, that picture is not a plasma. You can't call that plasma, because plasma is always in motion. You're reading more into the picture than what is there. Okay? The word plasma is a running boy, not a boy. Okay? Word plasma means flying eagle, not eagle. Okay? So if I take a picture of a flying eagle, what I have in the picture is an eagle, not a flying eagle. I'm putting more into the picture than what is there. All I have there is eagle, not flying eagle. And swimming fish, should I go through all the animals maybe? A fish, if I take a picture of a swimming fish, would I see a fish in the ocean or in the river or whatever, right, in the water? I don't see swimming. Swimming, if I want to take a picture of swimming, I need a movie. I can't take a picture of swimming. And you can't take a picture of ionizing. If the gas is ionizing, constantly ionizing, I'm not taking a picture of ionizing. I'm taking a picture of the atom, or an atom that has a little ball next to it, which is the electron little bead there. But I'm not taking a picture of plasma. I'm taking a picture of I can't take a picture of ionizing. Okay, that's the point. Okay, and these people have a hard time understanding that. So here, let's go with the state first. Okay, here we have plasma is not a state of matter. Move this over here.
Hey,
cover your face.
I want to talk.
Oh, okay.
So as we can see here.
So plasma is not a state of matter. Why? State is a static concept. And plasma is the one on the bottom, ionizing. So you can't take a picture of ionizing. Okay? Can't be a state of matter.
What about taking a picture of ionized in the past tense?
Yeah, again, if any picture I take, I'll have a static image. I'll have,
Will it
no
just be a
motion.
gas?
And the word ionizing and the word plasma both have are running.
Well, hold on. Let me stop you there.
Yeah.
There's a difference between burning and burnt. A burnt kangaroo isn't a kangaroo. It's a burnt kangaroo.
Yeah, there's no such thing as an adjective in physics.
Yeah, I got you. But
Okay.
but what would you call the chunk of just burnt meat? It's not burnt meat. What would you call it?
No, but I mean, first you have to identify the object. You can
Yeah,
say,
yeah.
that's a kangaroo. Now,
No,
if
no,
it's
no,
burnt,
no,
now
no,
you're
no.
going to talk about something else.
The burnt kangaroo.
Yeah.
What would you call it if it's not a burnt kangaroo?
No, I'm saying that there's no object called burnt
I know.
kangaroo. All I
Well,
have
what
is
would you call it then? If you
Well,
pointed, if you
after
pointed it at
after
it.
you point to the kangaroo, you can say the kangaroo is burnt.
No.
And
no, no,
the
no,
fish
no.
will be swimming.
It's not a kangaroo anymore. So you can't call it a
what do
kangaroo.
you call it? A bunch of carbon.
But it's not carbon yet.
I don't know.
What would
Whatever
you
you have
call it?
there. Well, I don't
Wouldn't
know.
it be easier to call it a burnt kangaroo?
Yeah, but you can call it a burnt kangaroo. What I'm saying is there's no object called a burnt kangaroo. Okay, there's no object called burnt. That's the point.
Yeah.
You don't look at the noun. You look at the adjective or the adverb and say, can I put an adjective, a verb turned adjective?
Well, by
in
that,
this case, right?
I guess by the same token, you could add an infinite amount of adjectives of where an object has been. You could say the object that was down the street 2 minutes ago. You could add a bunch of qualifiers that are almost irrelevant to what the object is now.
Yeah, and for
Whether
that,
it got burnt, whether it got moved, whether it got dropped.
But then what you're doing is comparing, because
Yeah.
burnt means that it wasn't burnt before. It's like dead and alive. You say, well, that's a dead cat, like Schrodinger's dead cat, but that means that you're comparing that against alive.
Okay.
You're making a comparison. But you cannot take a picture of the comparison of the concept known as burnt or dead or alive or whatever. You can take a picture of cat and then describe it and say the cat is burnt or whatever, dead or whatever. But my point is, there's no when you put an adjective and you say I can take a picture of a dead cat. No, you cannot. Not in physics. You can take a picture of cat, but not of dead.
But hold on.
Dead is
Okay.
You're putting more into the picture than what is there.
Okay, then one more question to
Yeah.
that. There are certain atomic elements that are man-made. Right?
Yeah. Uranium.
Well, not uranium. That comes naturally.
Well, after-
but the weird ones like Einsteinium.
Yeah,
whatever,
yeah.
Right? So those are
Lawrencium.
man-made. So we got Lawrencium.
Yeah.
But you wouldn't call Lawrencium because it's... You'd almost say it's a process because it's only there for a fraction of a second. So when you point at it, are you calling it what it is now or how it came to be?
Well, the point here is, again, if it appears in our world, in the physical world,
you can point to it and look at it.
Okay, for millions of gazillions of a second,
In
right?
that gazillionth of a second.
And you
in that
took a
frame.
picture. You
In
took
that
a
frame,
picture.
Yeah.
Let's say you were able to take a picture.
Okay.
There you have Lawrencium in front of you, right?
Isn't that like ionized gas? Because there was a process to get to it, like burning a kangaroo, but it is in front of you as it is.
Yeah, but the object that's in front of you
Yeah.
is a bunch of, in this case, under the rope model at least, you have all these balloons.
Yeah, it's a very
And so,
compact.
So yeah, you have this
ball of whatever.
multiple balloons. One.
It's a weird mass.
Right. It's got all the. You can take a picture of that and say that's Lawrencium. And you can take a picture of, I don't know, uranium and say, look, see how different they are, and say this is lawrencium, this is uranium, even though they, they're radioactive and they immediately.
But then why can't you have a picture of gas and ionized gas? Look how different they are.
No, because now we're talking about something else. Because again, in lawrencium, you're taking a picture of the atom, complex atom, a bunch of balloons. I can put a bunch of balloons together and say, look, this is what lawrencium looks like. And I take a picture of just a bunch of balloons, right? One inside the other, or tied, clown balloons, right? So I build this model and say, that's lawrencium. Okay, so I've got my model and I can take a picture of it. Nothing's happening in the word lawrencium.
Well, kind of, because
no, it's not.
It's about to explode.
We don't care how it got there, or whether the next second it disappears or breaks up or whatever. Okay. All we're saying is at a certain moment we have this lawrencium thing. We took a picture, and here's the picture of what lawrencium is or what it looks like or whatever. But you can't do that with plasma or ionized, because you're not talking about what is being plasma or what is being ionized. You're talking about the process. There, the word plasma includes motion. The word ionized includes motion. Ionized, when you put it in front of gas, it's an adjective, but it was a verb that was turned into an adjective. Ionization means you're pulling an electron out, right? So
kind of get it.
So
it's very.
The question, people think we're taking a picture of plasma. Yeah. No, you're taking a picture or trying to take a picture of ionized or ionizing.
It's not so much like lawrencium. It's really more like fire, where you think of fire, and if you take a snapshot of fire and zoom in, you can't really see the fire.
That's why fire is not a physical object.
You just see the atoms.
Fire is a process of combustion.
It's
okay?
Weird.
And so you can say, so we should use the word fire or plasma, because when you say plasma, say, well, plasma is a noun. No, not in physics. In physics, it's not a noun.
But it's weird because
fire is not a noun either.
Well, it is and it ain't. The reason why it is because, well, yeah, obviously fire is just like the breaking of light that gives it shape, but it isn't really something that has shape.
No, but it's not the issue of shape. It's that the word fire,
it's
right?
A verb.
We should replace it by what it means,
burning.
Which is combustion.
Or burning.
Burning oxygen or whatever. So you've got a verb, and you're trying to take a picture of the verb, not of the atom. Okay? Because if I put an oxygen atom there, and you say, well, that's an oxygen atom, no problem, an atom, right? You can take a picture of an atom, but you cannot take a picture of combustion. Okay? Combustion is a process. And so you need a movie for that. You can't take a picture of combustion. That's what people don't understand when they say fire or when they say plasma. That's weird. The issue.
Yeah.
So language is absolutely important.
But it's tricky to define those because it's a concept. Fire is a concept.
Yeah,
because you need
a concept.
Because
right.
You need a movie.
Yeah, you need a movie. Here you see it. In fact, there you see it. See, it's moving around. So so you can't have it as a state.
I feel like there's still something there, but I'd have to really dig deep into it to get a good question. I need a question that'll really stump people out.
Here you have plasma on the left-hand side. We all understand plasma because you're watching a movie, but you cannot take a picture of plasma because all I see there, I don't see ion. I don't see ionizing.
I get
what I see as atom is, if anything, I see electrons, but I don't see ionizing. For ionizing, you need the left one.
Yeah. There's still something there, but I can't get it yet.
Next
something still nags me, but I can't put my finger on it.
Okay, next movie, next week.
Next week I'll get you, but not this week. You win this time.
Okay, a couple more. Yeah. Okay, and then we go into the questions. Okay, here's the first one. Newton actually just proposed an inverse square relationship, a proportion, not an exact equation. This came after Newton. Absolutely right. Newton had no equations in Principia. Okay, he had no equations in there. All he did was have qualitative explanations. In that sense, he was more of a physicist than what you have today, because even though he knew quite a bit of math, okay, he was very interested in math in that sense. He was interested in how this universe works, and he was at least honest and says, "Fingo non hypothesis." He says, "I have no clue." That's what he said in Latin. He said he didn't know how gravity works, and he said it was just so strange that he would not be able to explain how gravity works from a distance without a mediator. And he could not explain that, but at least he was on the right track. Okay, but all he did in his book, he was explaining qualitatively that looks like this gravity thingy. It has to do with masses and the square of the distance, the inverse square of the distance. Okay, so That's all. He other than that, he said nothing more.
We have someone to ask. Hans, tell Bill to pause the GIF and ask him what it is, the plasma. But you already did that, didn't you?
What the plasma is?
If you pause the GIF, ask them what it is.
Yeah. What it is, we call it plasma because we use one word for it, but we cannot take a picture of ionizing. I want you to focus on that.
That's essentially what you did. You had the frame.
Yeah, I take the frame there, and what you have is in that picture. What you have is atom. We're going to go with a quantum version. We have the atom and an electron, right? That's what we have, and they're separated. They're not close together, they're separate. That's what we're staring at. So far, we see no motion. We don't know what's happening. We don't know that the atom lost that electron. We don't know any about that. We don't have that information in a single picture, in a single frame. We are reading more into the picture than what is there. Again, I like to use the case of the flying eagle or the swimming fish because when I take a picture of a swimming fish or a flying eagle, I'm not taking a picture of flying, I'm taking a picture of eagle. And when someone says, oh, that's a flying eagle. No, that's not a flying, that's an eagle. I can't take a picture of flying.
Yeah.
Flying, I need at least two. Then I can compare them and say, oh, this guy was here and then now it's over here. That's flying.
Yeah.
But in one picture, I cannot synthesize flying. You're reading more into the picture than what is there. Same thing with plasma. Plasma, you have the electron separated from its atom. Fine, no problem. But what do we have? We have an atom, we have an electron. That's what the picture shows.
Yeah, that's
objectively.
Full stop right there. That says it all.
That's all we have there. Now, ionizing, I need two pictures.
I think with that, you finally put it to rest, at least in my mind. Because, if you take a picture of ionizing, all you have is an atom and an electron over there. Yeah.
Okay, the last one here.
You're the one that says the atom is missing an electron, but that's motion. You're adding motion.
I'm adding motion. I'm reading more than what's there.
You're saying an electron was removed here. You're already doing detective work. But no, all that's there is an atom.
A picture, you cannot synthesize a verb.
Oh, yeah, I think I got you.
Okay, and here's the last one. The fellow says, prove you understand the normal accepted theories. Saying I'm a dumb brain, huh?
Yeah, you're dumb.
Then teach the audience why you believe that those are wrong.
There's a lot of words there. Prove, believe, and wrong.
Well, so I put prove, believe, and wrong. This fellow apparently comes from a monastery. That's probably where he did his schooling, whatever. He was part of the congregation.
I think that's all you actually do. All you do is explain the normal accepted theories.
Yeah, but
to the best of your ability. Well, to the best of anyone's, you actually do a better job explaining mainstream physics than mainstream physicists.
Yeah, but see this fellow talks about proof, belief, and he says whether it's right or wrong. Yeah, this is what he's talking about. All that has nothing to do with physics or science. It's got to do with religion. Where do you prove? Well, when you bring the good book, you convince the congregation, you say, oh, I have the evidence that the Lord has talked to me, or he's in communication with me when I'm in the bathroom or whatever, right? And so you show the book and you say, I have proof. And why? Because you're trying to make them believe. You're trying to show that everybody else is wrong except your religion or whatever, right? So we don't use prove, belief, or wrong, but you can see his language there. In science, we are only rational, okay? And what do? We do explanations, okay? And if you are not a scientist, otherwise you're not a scientist, right? And you are doing religion. If you talk about proof, belief, and what was the last one? And being wrong or right. What is wrong or right? An opinion, right? I mean, you're always wrong and I'm always right. So I guess my religion is better than yours, right?
Yeah, really, physics deals with hypotheticals in my mind. What science is all about is if this, then that.
Well, it's theories.
But that's what it boils down. Science, the shortest scientific what do you call it? Scientific method is if this, then that. You assume something, then you assume a relationship, and then you end up with a result. Then you look at that result and say, then comes the religion part. You say, is that really how it works? I don't think so. Let's try a different if this and that. And it's almost like with technology, where you kind of try a bunch of things until finally you find if that works, then that works, and then that you're satisfied with.
Yeah, and
that's how it works.
And again, everybody has a different satisfaction. This guy likes it. I mean, I can give you a theory, a very simple thing that I always use. You find the window broken, and the glass is on the floor. So you have the three people who didn't see what happened. They come up with theories of how that happened. One guy said, well, the dog jumped through the window. Another guy said, no, Johnny was playing soccer or baseball, and the ball went through the window. And another guy might say, no, your neighbor he hates you and came in there with a crowbar and broke your window. Yeah. So these are different theories, okay? The assumptions, one is the dog, the other one's the ball, the other one's the crowbar. Those are the assumptions. But then the theory is based on those assumptions. And that's the way it should work in science or in physics, especially in physics.
But that's why I like the if this then that, because the if this is the assumptions, then is the hypothesis, that is the result, but also the result tells you like how far off there the belief part comes in, because you could say an angel is what spins the earth. Right?
Yeah.
And a lot of people would be satisfied with that, but a lot of people wouldn't. But the satisfied part is the religion part, because you go, that doesn't sound right to me. It works as a hypothesis, until you dig, obviously, and I guess that's where the dissatisfaction comes in, where you go, that doesn't explain a lot. There's a lot here missing, so we have to work on something here.
Well, this is the issue. The issue is, I always say that religion, especially like Christianity, is more believable, more acceptable than general relativity, for example. Because in Christianity, you can say, look, let us assume that God exists, right? So you put a guy there and you say, look, this bearded guy, that's my God. So you can at least present your object, your things. You say, this is God, okay? No problem there. We all understand that. We see a guy with a beard with a magic wand, say, okay, I understand what I'm seeing. I comprehend. You can't do that with general relativity. General relativity says we start with space-time. Okay, show me space-time. What are you going to put a concept there and say time is bent? Is that what your theory is? I mean, what are you going to put for space-time? So I can imagine God, right? I cannot imagine four-dimensional space-time. And that's when they say, well, you're not supposed to take it so literally, and that's philosophy. They lose us. No. Show me space-time. Show me how it's warped, and then I'll understand your theory, let alone believe it. It's easier to believe in God. Believe.